Hey friends, it's Ben, and this is yet another video for the Calc 3 class. In this case, we're going to talk about the notion of Lagrange multipliers. So the thing that we're doing with Lagrange multipliers is that you have some sort of a constraint that you are placing on your function, and you're looking for maximums or minimums subject to that constraint. Okay, so let me share screen here in order to show you some pictures of what's going on with that. All right, and then I will make comment in passing. It is pronounced Lagrange. Actually, it's pronounced Lagrange. I think maybe in Texas it's pronounced Lagrange. So, all right. So the notion that we've got here is that you're asking for a maximum or a minimum of some function, and you have a constraint where your function, some other function of x and y is set equal to 0. The set equal to 0 is completely unimportant to this. Okay. It can be that the function is set equal to 3 or set equal to negative pi or whatever, because you can just subtract or add that value to the other side in order to make the 0 be there. It doesn't figure into the theory. So the way that you will tackle this is that you're going to stick with that constraint that you were given, and you're going to add a couple of equations here that are going to seem pretty weird. We introduce an extra variable lambda. And in what I wrote here, put my lambda to be multiplied by the f sub x and the f sub y, but you could just as easily have taken and put the lambdas over here to the other side and had them be multiplied by the g sub x and the g sub y. As a matter of fact, as best as I recall, that is how the textbook lists it. The value you get for lambda is not going to be important. It needs to not be 0, because if it is, it kind of goofs up a little bit of the theory stuff, but it does not tell you whether it's going to be a maximum or a minimum or anything like that. Lambda is just a dummy variable that you plug in there in order to get this problem to work right. I'll show you a picture in a second as to why that is. So then the other little note here is, if you're going to get both a maximum and a minimum, you would expect to have your g of xy turn out to be g of xy equals 0. That constraint should give you a curve or a surface or whatever you're dealing with that is bounded. If it is not, you may still get a maximum or a minimum. It's just that you're not guaranteed to have that happen every time. So keep that in mind with some of these things we do. And then here is kind of a neat part. If you were doing this with more dimensions than what I'm doing for my picture, then you could certainly just add in the g sub z and the f sub z for this. And hell, you can have it in 15 dimensions, okay? What's important is that you've got all of those derivatives being multiplied by that lambda on one side or the other. So graphically, here's the thing that we might think about. So I've got a constraint here that's something like g of xy equals 0. Maybe it's x squared plus y squared equals 1, you know. That's what's important here, is that it's some kind of a constraint. And then I'm looking at some function f of xy. Maybe it is something where if you set the function equal to a constant, like so, that you might have a line that's got a negative slope there, okay? But if you set it equal to x plus y equal to 2 or x plus y equal to -1, that you would have different places there, and you might be, you might be marching along there and getting these level curves increasing as you go along. So if you've got that sort of thing happening, at some place here, you're going to actually get a point of tangency between your constraint and these level curves of the f of x, y. And the way that you actually would find that place is that you would want to think about having the tangent line or well, what we really think about is what we refer to as the normal vector for those lines there. And what we don't write down here, because we've got a different kind of a setup than we had in different semesters, is that we would take the gradient of f and the gradient of g, and those would give us normal vectors, which are perpendicular to the tangent vectors, okay? And we say that we don't just want them equal to each other, but maybe some multiple of each other. And because that gradient thing that I'm trying to avoid actually working with, because it belongs in Calc 4 now, because it would be defined like so, then you get the lambda g sub x and set that equal to the f sub x and the lambda g sub y, and so on and so forth there, okay? So the thing that we put on the previous page is just going ahead and putting all of those together in whatever setting we happen to be in, 2 dimensions, 3 dimensions, 15 dimensions, right? So in any case, though, this little comment out to the side here at the point of tangency, the direction of maximum increase is going to be perpendicular to the tangent there for the g of x, y equals 0. And that's just a geometric fact that, again, has to do with vector stuff that we're trying to avoid a little bit in this course. So if we have that point of tangency, like here, then as we increase or decrease in order to get off of that point of tangency, we're going to end up having we're going to end up having stuff that lifts up off of that curve there. So consequently, you're going to get some sort of a maximum or minimum occurring because of that tangency there. So, all right, then continuing on, we're going to look at an example of this, all right? So the thing we're going to have is x squared plus 2y squared, and we're going to look for where that's a maximum on the circle x squared plus y squared equals 1. Now, you might also have a question that asks you to do this for the region x squared plus y squared less than or equal to 1, in which case you look in the interior of the circle by looking for critical points. And if you did that, you'll end up finding 0, 0, okay? But here we're specifically looking at what to do on the boundary, so subject to the constraint. So in doing this, we're going to have to get the f sub x and the f sub y, and then we're going to have to do the g sub x and the g sub y. Sometimes it may require you to do a little bit of thinking to figure out what the g of x, y actually is, but usually it's going to be pretty straightforward. Okay, so once we got the f sub x and the f sub x, f sub y, g sub x, g sub y, then we're going to say, I want my constraint to be true, and then I want my lambda times f sub x, damn it, I put them backwards this time. It shouldn't matter. Lambda times f sub x is equal to g sub x, and lambda times f sub y is equal to g sub y. So if you've got lambda times 2x equals 2x, your immediate instinct is to say, aha, cross out the 2x's. I'm going to get lambda equals 1. But x could also be equal to 0. So this bit here is just pointing that out, that if we move stuff to the other side and factor 2x, then you're going to get either this is 0 or that's 0, one or the other. If the first one is 0, then does it say if x is going to be equal to 0, then taking a look at our other two factors from the g sub y, because x is 0, y can't be 0, and the reason the y can't be 0 is actually from our circle here. If x is 0, then your y squared has to be plus or minus 1, right? And so we'll get the, that y squared equaling plus or minus 1. And then I wrote lambda equals 1/2, and that lambda equals 1/2 actually comes from this bit over here, okay? We don't care about lambda, but if x is 0, we can't have y be 0, so we'd have to have lambda be 1/2, and the y be plus or minus 1. So that tells you that from the x equals 0, you're going to get these points here, the 0 plus or minus 1. Now, if on the other hand, we went this direction and had lambda was 1, then we would substitute in over here and find out that 2 lambda minus 1 has to be 1. So that means that the 2y had to be what was 0. And so that has a little typo in it there. Great. 2 lambda minus 1 can't be 0. Okay, so therefore the y is equal to 0, and the x squared plus y squared has got to be equal to 1. And so if you've got y equal to 0 and the x squared plus y squared is equal to 1, then the x had to be plus or minus 1. And that is when you get these possibilities over here. All right. Then after you've identified these things that kind of act like critical points, quasi-critical, yeah, I don't know. But after you've identified them, plug them all in. Turns out the maximum occurs in two different places, where the points were 0, 1, and 0, minus 1. And the minimum occurs in two different places, where we had the x be 1 and, I'm sorry, where we had the point 1, 0 and point minus 1, 0. Okay. Sound good? All right. Then let's go ahead and take a look at another one here. All right, so this one asks us to find the maximum of this 8x minus 4z. Okay, so we've jumped up into 3 dimensions, and on this figure here. Now, if you went ahead and got an implicit plot from Calc 3D or something like that, you're going to see that this would actually turn out to be an ellipsoid. In other words, a sphere that's just stretched in one direction or the other. So that means that we've got something that is going to have both a maximum and a minimum because it's bounded. But we're really just interested in the maximum in this particular case. If you're wondering why it's phrased differently, I mean, there are just some problems where we actually are more interested in a minimum or a maximum. Economics or business type applications, you may have some sort of a profit function coming out here that's just linear, and you have some sort of a constraint that ends up being usually more complicated than this, for a business sort of setup, but you might have something that has to do with materials and production that ends up being nonlinear. Okay, so like before, take your partials. The f sub x is going to be 8, the f sub y is 0, the f sub z is -4. That suggests that this problem ought to be a lot easier, right? Your constraint is this guy here, and I keep saying the subtract 5 so that it agrees with how they do stuff in your textbook, but don't worry about it. Just leave the 5 over to the side, because as soon as we take the derivatives, the 5 just goes away, right? So you get your g sub x, your g sub y, your g sub z, and then you have to go back through and let the lambda be multiplied by one side or the other on those. I keep multiplying my lambda times the f. There's no real need for that. It can be times the g as well. But then for this, if you've got 8 times lambda equals 2 times x, well, then your x has got to be 4 times lambda. Okay. Here, though, we found out that lambda times 0 is 20y. Well, then y has to be 0. There's no choice. So then we've got here that the -4 lambda needs to be equal to 2z. So z is -2 lambda. That tells you that you've got a connection going on between your x and your z. So that's kind of nice there. But what I'm going to do, since I have x and z both in terms of lambda and y as just a 0, I'm going to go back to my constraint up here and just plug those things into it. So instead of x squared, I've got 4 lambda squared. Instead of y squared, I got 0. Instead of z squared, I've got -2 lambda being squared. That tells me that my lambda has to turn out to be plus or minus 1/2. And then I can plug it in and find out what my x is. And I wrote what my y is, because I can't write worth a damn. So let's go ahead and put that is z equals. If you notice, when I actually use it over here, didn't have any problem writing down the right thing. But as I was just writing, couldn't seem to copy the right thing down. All right. Anyway, though, so since I've got my 2 points that I'm going to deal with, my x, remember, was plus or minus 2. But because the z was the negative of 2 lambda, whereas the x was the positive 4 lambda, that means that the sign of the z is going to be the opposite of the sign of the x. And so we've got the 2, 0, -1, and the -2, 0, 1. We do not have to deal with 2, 0, +1 or -2, 0, -1. Those are not possibilities here. We plug in, one of them is my max, one of them is my minimum, boom, done. Okay. So let's take a look at then the more complicated end of things. So sometimes you may have to look for maximums, minimums with more than one constraint. So for example, I might be trying to look at something that is happening, and let's see if I can draw this real quick. If you take 2 cylinders and try to look at where they intersect, I have really done it for myself by promising to draw this. But the intersection of 2 cylinders, and sorry that it's kind of primitive looking there, is going to end up looking somewhat like that. The cylinders themselves, you can write an equation for super easily. X squared plus y squared equals 1 maybe, and maybe the other one is x squared plus z squared equals 1. Okay, so if you're looking at the intersection of those two things, the intersection is going to be these kind of elliptical things that are laying on their sides. And by dealing with this notion of the multiple constraints, you can do all of that kind of at once, and you don't have to kind of go through quite as much of a painful step-by-step process of getting each piece. So, okay. So, you know what? A better picture than this could be easily had, though, because I could have instead just drawn a quick cylinder and then a plane cutting the cylinder like so. Okay, so there's maybe an easier to visualize sort of thing. You could have a constraint like that and maybe a constraint like this. You know, that's much easier to write out and probably much easier to solve without using what we're doing here. But this is the notion of what we end up working out here. So the method that we have, we're going to have our two constraints that we have to solve things with regard to. But now, because there are two constraints, we end up introducing two dummy variables, lambda and mu. And so we will be doing a similar kind of problem. It's just that we end up introducing two variables into it to make it work out. So, quick example of that. So we're going to look at the maximum for this f of xy equaling x plus 2y plus 3z. And we're going to be on this plane here and this circle here. So, kind of like what I just drew a quick sketch of, right? All right, so then we take the f sub x and the f sub y on these. I'm sorry, we take the f sub x, f sub y, f sub z. Those turn out to be super easy, right? And it turns out the g sub x, g sub y, and g sub z are also pretty easy. The h sub x and h sub y, not too much harder, 2x and 2y. But the h sub z, because there were no z's appearing in the equation, you just get 0, all right? So we have constraint 1, constraint 2, and then we have that f sub x needs to be equal to lambda times g sub x plus mu times g sub y. So that gets a little more convoluted there. Same idea with the derivatives with respect to y, same idea with the derivatives with respect to z. However, when we look at the derivatives with respect to z, notice that the mu stuff drops out and we just have that the lambda has to be 3. We don't actually care what lambda is. But once we know what it is, we can just substitute it into the other places that it appears. And that means that you're dealing with a number, not another variable. So this one here turns into now 2 mu x equal -2, and then 2 mu y needs to be equal to +2. Well, gosh, that says that you can solve for x and solve for y in terms of mu, and since you get the negative of each other on that, then you've got your x needs to be equal to -y. Once you've got that, you could go over here into the x squared plus y squared equals 1 and substitute either one of them in there and have 2x squared or 2y squared, whichever you want to do. And you get that your x then is equal to plus or minus 1/√2. And then the y is just the negative of that. So that means that we've gotten 2 points out of that, not 4 points, okay? Then, once we've got your x and your y figured out for that, you can go back and plug into this x minus y plus z equals 1, and do a little arithmetic and find out that your z needs to be 1 minus or plus, and it needs to agree with the sign of the y. So 1 minus or plus the square root of 2. All right. So that says we've got these 2 points here, and we can plug them in to calculate. And I got to tell you, it just got awful just doing the arithmetic of that. So I just went ahead and grabbed my calculator and plugged in, because the values that you got are not going to be super close to each other. So getting an approximation with the negative 1.9 and the positive 1.9, that told me that the maximum, since that's the thing I wanted to look for, was totally right there. Okay. All right. So that's what you do with these Lagrange multipliers. They can get you answers sometimes when you couldn't get answers otherwise, though. For example, a common question to ask is, here's a plane, x plus y plus z equals 1, okay? What's the point on that plane that is closest to the origin? Now, there's no point that's farthest away, because you can always take points farther and farther away from the origin, but there will be a closest point. And you can solve it using this Lagrange multiplier thing of saying, okay, that means that the function I want to maximize, now that I want to minimize, is going to be either the square root of x squared plus y squared plus z squared, or just x squared plus y squared plus z squared. So you think about your level surfaces or spheres, and you really want to figure out the sphere that is tangent to that plane. So you set up your Lagrange multiplier problem and say 2x equals lambda times whatever the times 1, and 2y equals lambda times 1, and so forth. And it ends up being something fairly simple to solve there and get you the point that's closest to something. And that's kind of a common thing to try to look for physically, is the point on some surface, on some orbit, something like that, that is closest to something. Now, that's a very mathy sort of example where this is useful. Let me try to say something a little more sciencey. What is the point on the orbit of a comet where it is closest to the sun? Well, comets have hyperbolic orbits, and so you can say something about that orbit being a constraint of, usually they're on the ecliptic plane. Boy, I'm straying outside of my comfort zone, sorry. But they're going to be sitting on a certain plane, and they're going to have a certain orbit to it, and those are going to be two constraints. And so you can look at minimizing x squared plus y squared plus z squared subject to those two constraints. Less physically visualization sort of thing. If a company is trying to maximize their profits based on selling two resources, those two resources, then you can talk about X and Y being the number of things that they produce, and you'll have certain constraints based on production costs, based on labor costs. Those would be under production costs, sorry. But the inventories, if you have two items that happen to use the same inventory, if we talk about cars that Kia Motors sells, I've got a Kia. So the wheels that go on to the Kia Soul and the wheels that go on the Kia Forte, they're the same wheel, you know. So you have competing resources there within the company, and that means that there's a constraint based on inventory. But you end up having some complicated interactions between those where there's an optimal number to produce in order to get the biggest profit. But everything's based a little bit on guesswork there. but it's all really a constraint problem and a maximum minimum problem. It's just really complicated. The stuff that we do, I know, is a little bit hard, but it's not as complicated as the real life problems. If you end up doing something in finance or something later, you will work your way into it. It won't be that you just get dropped in. And so this is, believe it or not, the easier sort of examples. All right, I'll let you go. Talk to you in class.